Anodizing of aluminium. Anodizing is an electrochemical process for producing stable oxide films on the surface of metals. Anodic coatings are classified according to the solvent action of the electrolyte used to produce the anodic film. Sulfuric acid anodizing is by far the most important anodizing process due to the characteristics of the process and the properties of the film. Anodizing of aluminium is an electrochemical process in which the aluminium part is made, the anode. A potential is applied to this piece must be high enough to allow the development of oxygen on the aluminium surface. In anodizing, the coating is produced by reaction of the metal with the ions of the electrolyte producing generally a coating with greater volume than the aluminium substrate. There is normally an overall increase in dimension of the pieces after anodizing. For conventional sulfuric anodizing, this overall increase in dimension is approximately 1/3 of the coating thickness. The anodic film consists of two layers. The porous thick layer growing on an inert layer which is thin, dense, and dielectrical, and normally called barrier layer. The dimensions of the oxide cells are directly influenced by the anodizing conditions. With increasing voltage, cell size increases and the number of pores decreases accordingly. During anodizing, there is a chemical attack from the electrolyte to the anodic film producing pores wider in the outer than in the inner part of the film. The sulfuric acid process is by far the most extensively used all over the world. The common acid concentration is 15 to 20% by weight, according to the film properties required. Current densities are normally of the order of 1 to 2 ampere per square decimeter with a voltage 12 to 20 volts and temperatures 18 to 25 degrees Celsius for anodizing times of up to about 60 minutes. The thickness of the anodic film increases with treatment time. Initially, there is a rapid and constant increase in the actual thickness. Then, growing decrease in the rate of thickness growth. Finally, growing heads to a stage where the thickness remains approximately constant in spite of continued application of current. During anodizing, there are a continuous thickness growth of the anodic film and a dissolution by chemical attack. The theoretical value is proportional to the treatment time when anodizing at constant current density. Acid, it depends upon Faraday's law, which states that the oxide formed is proportional to the electric charge passed through the anode. The effect of an increase of electrolyte temperature is a proportional increase in the rate of dissolution of the anodic film, resulting in thinner, more porous, and softer films. In decorative and protective anodizing temperatures in the range of 15 to 25 degrees Celsius are normally used. If temperature is increased further, the maximum thickness is reduced to lower values due to the higher dissolving power of the electrolyte. The range of current density used in standard anodizing usually varies from 1 to 2 ampere per square decimeter. As the current density is increased, the film forms more quickly with relatively less dissolution by the electrolyte. Consequently, the film is harder and less porous. At very high current densities, there is a tendency for burning. This is the development of excessively high current flow at local areas with overheating at such areas. The effect of increased concentration on the coating characteristics is similar to temperature increase, although the effect of temperature is more important than that of concentration. The increase in concentration limits the maximum film thickness due to the higher dissolving power of the concentrate solutions. Sealing is the last step in the anodizing process and is essential for retention during service of the initial appearance of the anodized material. Water sealing produces little change in the bulk oxide film by increasing water content up 4 to 10%. It causes pore blockage and formation of various forms of hydrated alumina. Sealing is commonly done by immersion in good quality water, heated to 95 to 100 degrees Celsius at a pH of 6 for a period of 2 to 3 minutes per micrometer of anode layer. Anodic films possess useful properties, including clear crystalline coatings, high surface hardness, abrasion resistance, high corrosion resistance, ease of coloring, plus electrical and thermal insulation. And, as always, thanks for watching.